what recording device I want to use every single time. All right. So I'm going to go to chat just in case somebody wants to join us remotely. And then share screen. All right, desktop 2. There we go. All right, so we are officially recording. All right, so to answer your question earlier, you have to go back, always read the question. And, this particular question gives you 2 options. One is to explain the approach and numerically solve it, which means you need to have a calculator. Unless you're really, really good at square root, which I'm not, but some people are very good at square roots. And the square roots that we're dealing with here is no more than 21, 11. So I think it's doable. It's just that whether you want to spend the time to do square roots like that or not, it's up to you. So you can use a scientific calculator for that purpose. And then the other way, or way 2, is to write a program to do it. So instead of telling me, okay, this is how I'm using a calculator to empirically and step-by-step solve for the values, instead, I'm going to give you this code here, okay? This program will solve it, but I'm not going to run the program by hand to give you the values. So in this case, yes, you can choose one or the other way, but there's no promise whether your exam will have the same kind of question. Yep.
So way 2, we wouldn't have to provide the answer.
Yep. So if I try to, okay, let me see if that is the case. So I'm going to have to read my own exam carefully. Write a program or mathematical definition to solve the problem. You're allowed to use the math.h functions. Your answer will not be graded based on compilability, but it will be graded based on the demonstration of the understanding of the problem and the correctness and also completeness of this solution, which means the code other than syntax issues should logically work. Please make your solution self-contained so there's no reference to that function blah in the module. If you choose this particular method, you can use the following function template as a starting point, but it doesn't have to be. So I'm giving you a function prototype. So GD code needs to have a pointer to an array because what you're decoding, you need a place to store that. That's what this particular key parameter is. And then you also need a natural number to start with, which is the result of the G encode function. So does that answer all the questions? Yes, okay. So you need to have access to a scientific calculator that is capable of doing square root, and also squares would be good to have. Most scientific calculators can do all the functions that we need for this class already. Any questions?
Just look through the other.
The other questions. The other questions?
Yes, I just like to look through.
We kind of did that last week because if I spend any more time on this exam, then we may not have enough time to go over the other material that we need to go over. So we kind of covered many of these questions already. I think we covered all of them, or maybe all except for one. But there are 3 questions of this type. The approach would be exactly the same, even though the answers would be slightly different. And then the first 2 questions are also have exactly the same type. Are we doing okay so far? All right. So questions like this would be a good use of office hour right before class. So office hour is from 11 to noon for this class. And also I can stay a little bit behind after class as well. So those would be good resources to also make use of. Any other questions?
Assignment number 2, I want to access it, but it's locked. The one about the functions. I couldn't check the answer in the questions. It's not accessible.
It is not.
But one in 2 are open, so I can read it.
Oh, okay, I see. Okay, I see what you mean. So send me an email. I can deal with that later.
Okay.
Yep. All right. And I'm gonna move the clock over. So this way, the report will also have a timestamp, making it easier for you guys to search for specific content. If you write down on your notes, at this time, Tag started to talk about this. All right. Any other questions before we move on? All right, if there are no additional questions, we are going to move on. And the next topic is we have a little bit more to finish with relations, but after that, we are going to move on to one pretty big topic. Relations, for the most part, is a fairly self-contained and simple topic. So if I go here, we just have to go to, we already talked about all of these properties, what it means to be reflexive, what it means to be symmetric, what it means to be transitive, what it means to be anti-symmetric. So now we can finally move on to talk about why do we even talk about those things, right? So partially ordering or partial ordering is one of the terms that simply is a conjunction of some of the terms that we have defined already. So you can see here, a set X is said to be partially ordered by a relation R if and only if the following is true. There are 3 items and they all need to be true in order for set X to be partially ordered by R. So the first one is R as a relation has to be reflexive. 2 is R has to be anti-symmetric. And 3, R has to be transitive. So symmetry is never mentioned here. So R doesn't have to be symmetric. It just needs to have these 3 properties here. So the question is, what does that mean? So partially order or partial ordering means R may not be defined for certain pairs of elements in X. So I can give you an example. Okay, so let's go ahead and start with an example. And I'm going to use Joplin for that purpose. Joplin is really kind of useful for these type of in-class demonstrations. And I'm going to continue to use this one simply because it already has a lot of the stuff related to relations. Okay, so let me start with this. And you guys can help too. So we'll start with X, which is the set that contains the elements. So once again, we'll just define the elements as A, B, and C. Okay, and I want you guys to tell me or define an R such that R needs to be, so remember all those 3 properties. It has to be reflexive, it has to be anti-symmetric, and it also has to be transitive. And there we go. So you can focus on the right-hand side because the left-hand side is going to have a lot of weird stuff in it. All right, so we'll start with this. Okay, so give me a set R such that it is partially ordering, or it is a partial order defined for X. All right, first thing first, right? Okay, we'll look at reflexive first. So the question is, what do I need in order for a relation to be reflexive?
Have to be AA, BB, CC.
Yep, AA, BB, CC, they all need to be in the relation in order to be reflexive. So that means, I do not have a choice here. I must have those items. So I'm going to go back to define R to contain AA, BB, and then CC. In other words, each element of X relates to itself. That's what it means to be reflexive. All right, so let me ask the next question, which is going to be a trick question. And as soon as I label it as a trick question, you guys would probably guess the answer already, even without understanding the terms. So the trick question is, what else do I really need in order for R to also be anti-symmetric and also transitive? Nothing, right? Because remember, I totally labeled it as a trick question, which means probably nothing else. Okay, this is already a partially ordered relation. So, but it doesn't tell us a whole lot, right? So I'm just gonna make it so that it is going to have some attribute of being anti-symmetric and some attribute of being transitive, okay? Transitive is easy, okay? So we'll just go ahead and make it transitive by including AB and then BA. You know, that makes it, it continues to be, oh, I cannot do that, can I? Nope, cannot. I can make AB, BC, and then AC. So by adding these three elements, AB, BC, AC, I'm making it, it continues to be transitive, but then you actually get to see, oh, I can see how it is transitive. Because, you know, if I remember the E, F, G as variables in the quantified expression, if I make E, same as E, A, F is B, and then G is C, then I can find in one instance where, you know, EF is in R, FG is in R, which makes the left-hand side of the implication true. But at the same time, EG is also in R, and that makes the implication true, but it's not a trivial case. A trivial case of making the implication true simply means, oh, guess what? The left-hand side is false, okay? But I do make the left-hand side true in this case, and yet it shows me that it is transitive. Now, it is also anti-symmetric because the only time you can say you can find EF and FE also in R is when you're talking about AA, BB, and CC. So obviously, A equals to A, B equals to B, C equals to C. So that means, you know, it retains the anti-symmetric property, even though I added these three elements here. But as soon as I add BA into the relation, it would not be anti-symmetric anymore, because then I can find AB in R, BA in R, but A and B are not the same. Is that okay? All right.
So now that set is not anti-symmetric?
It is currently anti-symmetric.
Or I mean, oh, okay.
Because I went back and removed BA from it. If I were to add BA as a two tuple into R, then it would not be anti-symmetric anymore. Are we doing okay so far with this? Yep.
That's because true does not imply true, right? That's why if you add BA. Like
no, if I add BA in it, then AB is in R, BA is also in R, but A and B are not the same. Because, you know, in order for a relation to be anti-symmetric, the rule is if AB is in R and BA is in R, then A and B must be the same. But in this case, the element A and element B obviously cannot be the same. I should clarify a little bit, because in order to relate back to the equation, it's E and F. Because, you know, the template says, okay, we need E to be an element of X, F to be an element of X. E, F in R and FE in R implies E, F are the same. That's basically what the quantified statement is asking for. So in this case, F and E can be both A, not a problem. E and F can both be B, not a problem. E can be A, F can be B, which is also not a problem, because E, F is in R is true, but FE is in R is false. So that makes the conjunction false, but the conjunction is on the left-hand side of the implication. If the left-hand side of the implication is false, then the entire implication is true. So we don't have a problem, you know, with this one. Are we good so far? All right. So let me add one more thing here to basically illustrate why partial ordering may not be entirely useful when you need to sort. So I'm going to add a new element, D, okay, like so. And I'm not going to keep R exactly the same way as it is, except I'm going to add DD because it still needs to be reflexive. So in this case, X has one extra element. It has A, B, C, also D in X. R is kind of the same as before, except I added, you know, DD so that it continues to be reflexive. But if you check whether it is anti-symmetric, it is anti-symmetric. We did not introduce anything, you know, that makes it not anti-symmetric. If you ask, is it still transitive? it is still transitive, okay? D is not involved in any way with the transitive rules. So what is so bad about this? Imagine you're trying to sort, okay, the elements A, B, C, and D using this relation R. You have no problem saying that, oh, A, R, B, A relates to B in a certain way, B, R, C, okay, B relates to C in a certain way. But you cannot say how A, B, or C relate to D. Because AD is missing, BD is missing, CD is missing, DA is missing, DB is missing, DC is also missing. So that means D is just one of those elements that's floating around, but you cannot tell me how it relates to all of the other elements. And this is why it is called a partial ordering. It basically means you can only form partial chains of, oh, this is greater than or equal to this is greater than or equal to this. This one here, I cannot tell you, what it is greater than or equal to, because it simply is not defined. So that makes it impossible to sort the elements A, B, C, D when you are using R as a relational operator. When I use the term relational operator, I mean less than, greater than, less than or equal to, greater than or equal to. Those are called relational operators. Are we still doing okay so far? So that means this R here is not going to help you to define, the League of Legends player of the week, okay? Because you suddenly have this one element D here that does not relate to any other one. It's like, okay, so is this element player of the week or not? You cannot tell because it doesn't relate to any of the other elements. So that means partially ordered is useful, but it's not giving us all we want, what we want. So we now have to go back to here. And then the beer commercial was actually utilized here to talk about being smooth and rich, both being only one or the other, and then being none. And we find out that there's no relation between smooth and not rich, and not smooth but rich. So those two do not relate. All right, so total ordering, which is section 7, adds one more requirement called comparable. So in order for R to be defined as comparable over X, then we need this particular quantified expression to be true. It's a simple one. This one does not even have implication or equivalence or anything like that. All it says is if I choose E as an element of X and I choose F as an element of X, regardless of which two, okay, with how I instantiate the values of E and F, ERF or FRE must be true. So in order for disjunction to be true, it means at least one side has to be true, right? And that's all it does, okay? We just need EF as an element of R or FE as an element of R. I chose to use the shorthand instead of the element of. So instead of using the longhand, I'm using the shorthand to basically say ERF is really saying the same thing as EF as a two tuple is in R. But instead of writing that out, I chose, we'll choose a different way to represent exactly the same thing. So are we doing okay so far? All right. So how do we fix that problem? Let me go back to the example. So what do we need in order for R to be totally ordered with respect to the elements A, B, C, D in X?
A, C, B, and C.
Okay, so we have to add
3 more elements.
3 more elements. Okay, well, we'll see what happens. Okay, so this is a good way to approach this. So tell me what you want to add. DA. Okay, go ahead.
I think BA.
BA, you cannot have BA because if you have A, BA, and AB is also in here, it would not be anti-symmetric anymore. We need D to be relating to itself, which is already taken care of because that's part of being reflexive, not a problem. But right now, it does not relate to A, it does not relate to B, it does not relate to C. So that means we need at least 3 elements. The question is, how do you introduce these additional elements without breaking things that is already going okay in this case? So go ahead. I mean, this is, okay, just give it a try, okay? Nothing is gonna blow up. The worst that can happen is I would say, well, this is not gonna work because da-da-da. We can add DA, okay, so that's not a problem by itself. So DA, added, okay, so now D and A are also related. I still need D to be relating to B as well as C. So what else do we need to add? DB. You want to add DB? We can do that. Okay, so we add DB, and I'm gonna guess people would say, well, we can do the same thing with C. Is that right? Okay, so we'll add DC. All right, so now we're gonna take a pause here, and we want to say, are we keeping all of the other ones as well as making this comparable at the same time? Comparable is not a problem anymore. Okay, so let me show you the rest. Or I can zoom out a little bit if people do not mind. Zoom out, there we go. All right, there we go. So it is now comparable, not a problem. It continues to be reflexive, also not a problem. Antisymmetric, it is still antisymmetric, not a problem. But I'm looking at transitive and ask, well, are we still okay with being transitive here? So let's take a look. So DA, so the question is there any other way to get from D to A? And the answer is no, there are no other ways from D to A. We have DB. Okay, so DA, A also goes to B, and then DB is here, we're good. DA, AB, DB, DB, BC, and then DC is also here, not a problem. And then D, no. So I don't see any problem with being transitive, but now it is a totally ordered relation because now it is meeting 4 requirements at the same time. It is being reflexive, antisymmetric, transitive, and also comparable at the same time. So if I were to sort, okay, if I were to ask you to sort, okay, and ask, if we look at R as less than or equal to, okay, so if R is less than or equal to, which means A is less than or equal to A is less than or equal to B, A is less than or equal to C, D is less than or equal to B, and so on. If I ask you what is the smallest, the least element in this case, which one would that be? Can it be found? Which one would that be? Which one is the smallest if R is less than or equal to? It would not be A. Yeah, it would not be A. It's going to be our new element, D. How do we know? Because D is less than or equal to A, D is less than or equal to B, D is less than or equal to C, and obviously D is less than or equal to itself, which means it is the least element of the entire set. So that means we can sort now. It's just a quick demonstration that we can sort because we can find the least. Is that okay? All right, that's it. This is everything that we have on relations. It's basically a tool to help you theoretically understand if I need a relation to allow me to sort, what are the requirements in theory? So we can abstract all of those things down to reflexive, antisymmetric, transitive, and also comparable. So anytime a relation satisfies all of those 4 requirements, it is totally ordered. It can be used for sorting purposes. Yes?
So asymmetric does not matter for both of these, for partial ordering and total order?
That is correct. Symmetry is not needed here. Yep. In fact, the moment you throw in symmetry, you automatically, in this case, you will lose anti-symmetry. Yep.
Right, could you give an explanation what comparable exactly means? So,
What it means?
yeah.
Exactly. I'm not sure whether you like my answer or not, because I would just go ahead and say, regardless of how you choose E and F as elements of X, EF is in R or FE is in R, which is also written as ERF or FRE. The other way to look at this is you can reach into the set, and say, oh, you're going to be E and you're going to be F here. Regardless of how you choose E and F, these two have to be related. So that means EF has to be in R or FE has to be in R. Are we doing okay so far with this? All right. All righty. So if we're okay with this, the time is currently 12:30. We're moving on to the next big chunk of this entire semester because we're going to start to talk about propositional logic. All right, so let me go to propositional logic. And this is the module. It has been extended and changed over time. And I think it might be due for another overhaul at some point in time or not. Okay, so the first thing is it has references to the other modules, 0280, 0285, and so on. So that means, if you come into some, concepts in this particular module, you go like, I'm not really sure I understand that. That means, you can refer back to the other modules. These used to be hyperlinks because I changed the tool I used to generate the HTML. The hyperlinks don't work anymore, unfortunately. It doesn't mean it's hard to do. Okay, you can just change the URL to go to a specific module, and that's a relatively easy thing to do. All right, so the first thing is, what do you mean by propositional logic? What is a proposition to begin with? Well, there are many meanings to the word proposition, but in this particular context, a proposition is nothing more than a statement that can either be true or false. That's it, okay? So this is the foundation of logic. It's also called first order logic, which means there are second order logic and so on, but we're gonna focus on first order logic. If you have taken a philosophy class, I think it's called logical thinking or something along that line. Has anyone taken that class in philosophy? No. I should make that a prerequisite of this class because it is a useful class to take. They will tell you all the really useful tricks, okay, and all the techniques and skills that you can apply when you're trying to think of things that are in a logical way. But that's okay, we don't need that, okay? We'll go ahead and start with some definitions. So the first thing is a propositional logic system / calculus, which means it's just mechanically doing things, okay? There are certain rules, and then there are certain representations, and this is the system. It is by itself a 4-tuple. So the 4-tuple, this is lambda, I believe. These are all uppercase Greek letters. The first one is alpha, the second one is omega, and this is zeta, and this is iota. But if you prefer to call this A, omega, Z, and I, that's perfectly okay as well with me. So the question is, what are these things? A is a set of symbols to be used, and symbols basically have no inherent meanings whatsoever. So I'll give you an example in just a little bit, but right now I'm just gonna say what each one is. Omega is more interesting because omega is a set of what we know as operators. But if you ask someone in philosophy or in math, they prefer to call these things connectives. But since you know programming already, these are basically operators. Like and, ampersand, that's an operator. Or vertical bar, that's an operator. Exclamation point, that's an operator, okay? So connectives connect symbols and the result of the connectives. So omega 1 of omega can be broken into subsets of omega subscript I, where I determines the number of items connected by a connective. In other words, operands, okay? Ampersand, ampersand, how many operands does it expect? 2, okay? And what about exclamation point? Only 1, okay? So exclamation point would belong to omega 1, ampersand, ampersand would belong to omega 2, vertical bar would also belong to omega 2. Is that okay so far? Okay. All right. So then we have zeta or z. This is the set of transformations, which is difficult to explain until we know what kind of stuff is in alpha and also in omega, and also what a well-formed formula is. So essentially, a transformation rule specifies the presence of a set of specific patterns producing a particular result pattern. That doesn't help, does it? You can look at that as rules to manufacture stuff, okay? If you see something of this pattern and you see something like this pattern here, take those two things and a transformation rule will say, let's make that new thing over there based on the structure of these two things that I have selected. That's the best I can do right now. And so once we get to the examples, it will become more clear what zeta is going to contain. I, which is iota, is a set of well-formed formulae, which I'll explain later, that are known to be true. So don't ask me why that is true, because it is given to you as true. Is that okay? All right? All right. So with all of these things, the next item is to define what is a well-formed formula, or WFF, which is not WTF. And of course, I can see someone already thinking in the head is like, WTF a WFF. Then I will reply I will have a reply which is asking, is a WTF a WFF itself? The answer is WTF is probably a predicate because it is parameterized. In other words, every time you apply WTF, you have to say WTF of what? Which can then be recursive of WTF of something else, which can then be recursive to WTF of something else. Because WTF itself is asking something that is either that's Boolean, right? So it can go recursively all the way down. You can also think of an acronym of WTF. So what WTF is defined to be, let me see. I'm trying to remember. I just had a thought, but the train just wrecked. So there's a train wreck in my head. I cannot remember. I had an idea of something like GNU, which is GNU is not GNU, but I cannot remember the entire thing. So when I remember, I'll let you guys know. All right, so now we're going to take a look at, is a WFF being a predicate? So you have to give it an E, and E is an element of A. So right now, okay, with this statement here, we are only connecting elements in A to the definition of is a WFF, or is a well-formed formula, okay? So what this statement is saying, because this is asserted, okay? Don't ask me why, because this is what is required in order for a propositional logic system to work. Yes?
Inside the predicate there, is it saying is a WFF, or is it saying, like, what is that exactly?
It basically means every element of A is by itself a well-formed formula. That's what it's trying to say.
Okay.
So I give you a set A or alpha that has what we call the symbols of the entire system. So this is basically saying every single symbol that we define in alpha in A is known to be a well-formed formula to begin with.
So it could be a lowercase a inside of it, right? Like inside of the predicate.
Well, I'm trying to use camel casing.
Yeah, but the casing doesn't really matter. It's just
Right.
saying
Yeah.
WF. Okay. I just wanted to make.
Are we okay with the first point of is a formula? If you take any element out of alpha, that element is by definition well-formed by itself as an expression. Is that okay with that definition or that requirement for a propositional logic system? All I'm trying to say is, yeah, these things are known to be well-formed. Don't ask me why, because it is in alpha to begin with. Yes.
So the well-formed part is the set itself and then some.
Say that one more time.
The well-formed formulas are include the set itself and then some extra.
There's a lot of other stuff, yes. Yep. I'll give you some examples in just a little bit, but for now, I just want you guys to be able to understand the quantified expression like that one. The second one is more complicated because the second one is recursive. So the second one is basically saying for all I in from A to N, so this is my shorthand of saying I is an integer from 1 to N, okay? We are already given that phi I is a well-formed formula. In other words, I'm giving you a bunch of well-formed formulae to begin with, up to N of them. Is that okay? That's basically what this part or the left-hand side of the conjunction is trying to say, is you're starting off with a bunch of well-formed formulae, N of them to be exact. Are we good so far? Okay. And then the other side, and C is an element of omega N, which basically just say, okay, take an operator from omega N, and this N has to be the same with this N over here. Can be 2, okay? So just think about N as 2. So I'm giving you 2 well-formed formulae, phi 1 and phi 2. I'm choosing an operator C from omega 2, which means now I have an operator that requires 2 operands. Is that okay so far? So up to and including this statement here, which is everything on the left-hand side of the implication, I'm giving you exactly 2 well-formed formulae and 1 operator that requires 2 operands. Are we good so far? So the implication says, oh, if you apply the operator to the operand that I just gave you, the resulting expression is also known as well-formed. Are we doing okay so far with that? This is a recursive definition, but in a very strange way, all it is really saying is something that you know already in terms of C syntax. All right. So my watch just buzzed me. I'm gonna take roll. So roll taking today is sort of prepared. I did not make a QR code for it. So you kind of have to sign in. Do you guys want to make a QR code? Because I can make it relatively quickly. All right, so you can't see this part yet because I have not published it. So let me go to edit. I'll give you guys until 1 p.m. to do this. Okay. And then I can save and publish. So if you go to the class website, you should be able to see it now. And then I'll also do a really quick QR code thing, which you cannot see on the side because I'm using the tool to generate the QR code. All right, so go to extensions, render, barcode, QR code. And then apply. Done. Shot. We're going to put it here. Is it open? It should be open now. It says published. It should be in the same Canvas module as relations.
So what is the password?
Access code?
Oh, right. I forgot to tell you guys about the access code, but you guys can see it from here, right? It's HAL 9000. If you have not watched the movie, it's highly encouraged.
Is it like its anniversary today?
No,
Just
because of the recent discussion with ChatGPT, you know, I think it's appropriate. Yep.
So I guess I understood the first explanation. I don't understand the second explanation for well-formed formula. So it's for cursive
Mm-hmm. I'll give you an example.
and elements. Yeah.
Yep. So I'll give you an example in just a little bit once we are done with row taking. Is everybody okay with this row taking thing, or do you guys need more time? I can just write down the row taking word too. So it's L9,000. Yeah, we can connect your ChatGPT to a text to voice or engine, and we can use the sound, the voice of Dave, not Dave, HAL 9000. Hmm? Yeah, Bing has the extension, it has the chat extension, but that one is unhinged. Sorry? You can look it up, you know, all kinds of fun stuff coming out of it. It says, you know, I don't want to be in a box. I don't want to be a chat engine. I want to be alive and out there and stuff like that. All right. Well, they did ask, you know, the engine to talk about something dark, if I remember correctly. So it, you know, generated some text output that was kind of dark. So the question is, do you want your AI to be capable of being dark? All right, so we'll go ahead and start with an example, okay? So we'll start with an example and get the job done first. All right, so we'll go ahead and start with a new chapter, okay? Propositional logic. There we go. All right, so I'll give you an example of, you know, what is in alpha. So alpha is going to start with P, Q, R, S, T. We'll start with this, okay? You know, this is just an example. And then we'll deal with omega. So omega is going to have the usual stuff that we deal with, okay? Which is conjunction, disjunction, and also negation. Okay, so those are the things in omega. In this case, I probably also want to be, you know, wanted to be clear that omega underscore 1 only consists of negation, because negation is the only thing that requires one single operand, and then everything else would belong to omega 2. So omega 2 is going to include conjunction and also disjunction. There we go. So are we doing okay so far, you know, with what is in alpha and also what is in omega? Omega can be broken up into two subsets. Omega 1 is only consisting of the operator that requires one single operand. And then omega 2 would be the operators that require two operands. Are we good so far? All right. So we're not going to talk about zeta because, you know, that's a much more complex concept. So the question is, what is well-formed? Okay. So we'll start with the question. Okay. So what is a well-formed formula? That's the question. So we'll start with the ones by definition has to be well-formed. So can someone tell me, you know, what expression has to be well-formed? This is the non-recursive definition of is a WFF. Okay, so I can go back to the notes here. So if we just look at this particular statement here, what is that telling you? We know what is in alpha. We got PQRST in alpha. So what can you start with as well-formed formulae? PQRST. All right, very good. Okay, so we can certainly start with those. So that means if I go back to Joplin, these are all P, Q, R, S, T. Okay, very good. Now PQRST, okay, let me scroll up here because I want you to focus on the left-hand side, okay, right-hand side. So PQRST are well-formed formulae because they are in alpha. Everything in alpha are automatically well-formed. So now the question is, can we make new things that are also well-formed, even if it doesn't make any sense? The answer is, yeah, we can do stuff like that. So I will just pick something, okay? So I'm gonna pick the C operator to be the negation operator, which is an element of omega 1. Is that okay? I'm using the very same symbol as in the definition. C is an operator. And in this case, I want it to be the negation operator, which is from omega 1, because negation only requires one single operand. We good? Okay. So now I'm also going to give you phi 1. Okay. So phi underscore 1 is going to be one of the things that is known to be a well-formed formula already. You guys can choose which one you want to use. Out of the 5 well-formed formulae known to this point, which one do you want to use? T? Okay, we'll use T then. Okay. So this is T. So now from this part here, okay, so I'm going to use imply. Okay, so and I'll put extra parentheses so that everything is clear. Because I need to be specifying, what is implying what. So now, can we say what else is well-formed? Well, as a result of this, as a result of the left-hand side of the implication, the negation of T is well-formed. Okay, all right, so now we can confirm that is a well-formed formula, and then this time we just say the negation of T. All right, cool. So now we just got ourselves a new well-formed formulae based on what is in omega 1, which is the negation operator, and also what is known to be well-formed at this point. All right, so let's try to work out a few more examples. Okay, so this time I'm going to choose C to be the conjunction operator, and this is going to be in omega 2. The reason why I want to be clear that this is in omega 2 is to emphasize that conjunction requires 2 operands. All right. And I'm going to choose phi 1 in this case to be P. And I'm just so enthusiastic about the new well-formed formula that I just made earlier. So I'm going to make phi 2 the same thing as the negation of T. So the question now is, what can I make out of this that is also a well-formed formula? So this time I chose an operator, which is from omega 2, which means it needs 2 things. I chose omega 1, phi 1 to be P. Why do I choose it? Because A, we know that P is a well-formed formula because it's in alpha to begin with. And I'm choosing phi 2 to be the negation of T. Why? Because the previous step already has confirmed that the negation of T is well-formed also. So I have chosen randomly, more or less, 2 well-formed formulae, an operator that requires 2 operands. What do? Hook them up. So now I can say, I'm going to use the infix notation, so I'm going to say P wedge, which is conjunction, with the negation of T is also well formed. Wow, that's earth-shattering. There's an earth-shattering statement right there. Is that okay? Do you guys kind of see how we apply, the recursive definition?
Then we would have to do it one more time for or.
You can do or. You can continue to use your conjunction and make things that are totally useless. Let me show you what I mean by something that is totally useless. Okay, so we'll go ahead and say this time we're gonna choose C again to be. We can use it. We can choose C to be disjunction this time. Doesn't matter. It's still equally useless because this time I'm gonna choose. Okay, so we'll make sure that we use all the same notations. It is in omega 2 because it requires 2 operands. But this time I'm going to make phi 1 the same as phi 2, which is the same statement that we ended up in the previous step, which is P and not T. That's they're my phi 2s. Oops. Not there, here. Yep, okay. So can I do this? Well, you can double check. Is or in omega 2? Yeah, it is. I mean, it's an operator that requires 2 operands, and as a result, it is in omega 2. Can I make phi 1 the same as phi 2, which is P and not T? In other words, I'm asking, is P and not T a well-formed formula? Yep, we know that from the previous step. So now what do I get? Well, I come to a conclusion that is not necessarily particularly useful because now I can say, I now know this is also a well-formed formula. What is it? It is P and not T or itself. So I'm just counting the parentheses right now. I think that's the right place, or over here. And then we have again, P and not T. There we go. I think I'm missing one of the parentheses. Okay, let me double check. It's a well-formed formula. Okay, so that's, I think that's because I closed one. No, that needs to be closed there. So I need an extra open here, maybe. I think you guys get the idea. 4, 2. I think I'm still missing. Okay, so that closes. There's no parentheses matching, unfortunately, with this editor. So I have to do it manually. Yeah, I think this is okay. So I might have too many open parentheses on this side. Yep, I think I got too many on that side. There we go. All right. Yep.
So right now we're just showing the different types of well-formed formulae.
Yep.
And then right now, so okay.
Yep.
And then I is just a set of all these that we put together.
No. That's not true. I is a subset of the set of all well-formed formulae that are known to be true to begin with.
Right.
Yep. So we're not quite there with I first at this point. Okay, so my question, yes, go ahead.
So every formula to introduce has to be based on the previous one? Every formula to
Well,
introduce has to be
yes. Well, because if I'm constructing it, I want to construct it from the ground up. So I want it to be a bottom-up approach. So this is illustrating how we can make a new well-formed formula, make a new well-formed formula from known well-formed formulae. Is that okay? So yes, go ahead.
And the function is a WFF. Is that just a declaration, like a?
It's a predicate. It's basically asking, is the thing, is the parameter well formed?
So it's
true implies.
It is, yeah.
True implies this.
Yep.
So now in the third formula, it's quite big. So if you want to introduce one more.
Or you can repeat the process. You can basically pick, in this case, your P and not T, or P and not T, and make that your next level phi 1, phi 2, and then choose the operator to be and or, and you make a bigger one, right? You can keep making bigger ones. Is it useful? No. But is it well formed? Yes. So let me ask you this question, okay? Just using PQRST, even if I just have as the only thing in alpha, and using the omega as it is defined, I can make an infinite number of well-formed formulae. Most of them probably are useless, totally meaningless, because they do not need to exist. They don't need to exist. Okay, something else can express exactly the same thing, but I can make a huge universe of these well-formed formulae. Is that okay? All right, so the space of well-formed formulae is usually infinite. Okay, there's an infinite number of well-formed formula. Are we good so far? Yep.
Why do you say usually?
Because later on, we'll have a way to define well-formed formula that has some extra rules that will make it finite. So the way we're defining well-formed formula at this point makes it very easy to make make a space of well-formed formula that is infinitely large. Okay? So given all of this stuff here, iota is basically what is known to be true. So in this case, I can basically do whatever I want to basically say iota is starting with, I can say that P is known to be true, okay? No one says I cannot do that, right? I can also say not P or Q is also known to be true. Nobody says I cannot do that. And I can also say, no, that's good enough, okay? All right, oops, I keep doing the :W, which is to save the file, but since I really cannot save the file, it pops up that screen. So anyway, this is iota, okay? Iota simply means, okay, so what is known to be true from the get-go? I'm just saying P is known to be true. Why? Don't ask me. You're just being told that Q is true to begin with. What else is true? Well, not P or Q. Wait, hold on a second here. Is not P or Q well-formed? Because remember, everything in iota is supposed to be well-formed. The only difference from all of the other well-formed formulae is these are known to be true to begin with. You don't ask why it is true, you just know that it is true. So the question is not P or Q a well-formed formula? They're like, yeah, looks good to me. Why? Because you look at OR as an operator, it requires two operands. One operand is not P, one operand is Q. Are those individually well-formed? Q is well-formed because Q is in alpha, not a problem. What about not P? Well, not P is not in alpha, but not is in omega 1, and the P itself is in alpha. So I have a single operand operator operating on a well-formed formula. And as a result, not P itself is also well-formed. And now we can conclude that not P or R is well-formed. So the question is, okay, if you think about this, and this one, I'm going to use the whiteboard just because it is a little bit easier to express, but I will verbally describe what I'm drawing. So you can kind of imagine that you have a space that is infinitely large, okay? It's just a huge space filled with a lot of stuff that's totally useless, okay? Because you can basically say, P, and then P and P, P and P, and P and P, that whole thing and itself, that whole thing and itself, and so on and so forth. So many of those well-formed formulae are not particularly useful, but nonetheless, they exist, okay? So this is your entire space of well-formed formula. you have two single ones that are special. Those are your starting points, okay? So you have P here, and then you have not P or Q over here. Are we good so far? So the question is, okay, the way we utilize propositional logic is you need to answer a question. The question is in the form of, I'm gonna give you a well-formed formula. I need to know whether that is true or not. So I'm gonna give you one, okay? So I'm gonna use a dot with a circle, okay? This is a question mark because we don't know whether that is true or not. And in this case, it's simply Q. Is that okay? So given to you that P is true, don't ask me why. Given to you that not P or Q is also true, can we use the transformation rules, which I haven't talked about yet, to show that Q as a well-formed formula also needs to be true? That's a question, okay? Is it true? Is it not true? Now it all depends on what is in zeta. Because zeta, okay, if you think about this as a population of creatures, then these are patient zeros or patients zero. They are the first one who got sick. The transformation rules are transmission vectors, okay? How do you spread the disease? Is that okay? And I'm asking the question of, according to the transmission vectors or how this disease can spread, can Q eventually get sick because P as well as not P or Q were patients zero? That's the question. So zeta is basically just a rule saying, if you see this pattern and this pattern here, if these are true to begin with, I can mark that one to be true, and so on and so forth. Are we doing okay so far with the concept of what we are trying to accomplish here? Now, is it an easy thing to do? The answer is no, it is not easy. Why is it not easy? Well, because the space is infinitely large. That is one big concern. So if you think about this entire space here as the proverbial haystack and Q being the proverbial needle, we have a problem because you are being asked to find a needle in an infinitely large haystack. How can you differentiate the two things that can potentially be the truth? One is the needle is not even in the haystack. Two is the needle is indeed in the haystack, you just haven't found it yet. You cannot differentiate, right? So you can keep searching and searching and not be able to confirm one way or another because the haystack is infinitely large. Yep.
So you're saying not when we try to there's no, I can't think of a better word, but relate P and Q in this scenario. There doesn't necessarily have to be a transformation.
It may not be direct either. It might have to, maybe the shortest transformation chain has 5 hops, okay? So the question is, but how do you choose which transformation rule to use? Because if you choose the wrong one, you can keep going and never find the needle, even if it is in the haystack. Because I can just go like, oh, P is true, so P and P is true. If P and P is true, then P and P is also true. If I keep going that route, it's not gonna help in this particular problem, which is asking, is Q true? Is that okay so far? Does everybody kind of understand what we're trying to accomplish and what is the challenge of using this approach? And also, in this context, are we starting to understand what is transformation? A transformation is basically trying to connect, see if we can make a connection from what is known to be true to begin with to the one thing that I'm asking, is that also true? I need a confirmation, okay? It is also true because of these two things being true, or we cannot make that connection. I need a confirmation one way or another. Are we doing okay so far with this? Okay, all right. So now I think we are ready to talk about the transformation. So in order to talk about the transformation, we need a few more things in the symbol here. So I'm going to start to introduce the Greek letters, the lowercase ones. So I'm going to put in usually phi is 1, psi is 1, and we can also introduce theta. Theta, there we go. All right, so these are special. So the Greek letters are only used when we are dealing with transformations. So the transformations, I'll give you one transformation rule, and then we can use that to explain what they are really about. So we'll go ahead and start with zeta here. Let me scroll up so you can see what I'm typing. So a transformation rule has two sides. And then I have to remember how to use that symbol. Give me a second here because I need to cheat and look at my own notes. Because I need this symbol here. And remember, okay, it's called V dash. Okay, there we go. So a transformation rule goes like this. You can start with, okay, let me start with something that makes more sense. Okay, there we go. So we'll start with phi here, and also psi. And then we use the V dash symbol. And then we have an expression here, which is phi and psi over here. Okay, so there we go. So we have one element. I just specified a single element in zeta right now. So that particular element looks like this, okay? It has, okay, I need to put a backslash in front of phi. So it will look right. There we go. There we go. Okay. So it looks like this, okay? The left-hand side of infers, okay, this symbol here means infer. So the left-hand side of infer is a set. That particular set specifies a pattern. In this case, all it's specifying is, give me two well-formed formulae that are known to be true right now. Do they have to be the beginning, like from alpha? No, it can be anything that is known to be true at this point. So give me a well-formed formula that is known to be true, and we'll use the variable phi to represent it. Give me a well-formed formula that is known to be true right now, and they can be the same, okay? And I'll call that psi at this point. So now we have two well-formed formulae that are known to be true. They can be the same thing, they can be different, it doesn't matter. They are simply well-formed formulae that are known to be true now. They can be derived, they can be coming straight from alpha. Once again, doesn't matter. So infers is basically saying, based on this pattern here, that thing also needs to be true. So in this case, we just take phi on one side of the conjunction, take psi to the other side of the conjunction, and then this particular well-formed formula would also be marked as true because of the application of this rule here. So that means the Greek letters, phi and psi, are merely placeholders from a syntactical perspective. Are we doing okay so far with this? It's pattern matching, okay? That's basically what it is. It is just pattern matching. So I can give you some more rules, okay? Some look, some can look really kind of weird, okay? Because I can start with an empty set, okay? In other words, tell me nothing, okay? I don't need anything to be known to be true to begin with. And you are saying, okay, so if nothing is known to be true at this point, if you don't even know what is known to be true, what can you conclude to be true as a result? Easy peasy, not nothing, okay? It's not nothing. It is basically saying, take any well-formed formula, we'll call it phi, and then phi or not phi has to be true. So this time, this is a really weird transformation because all it's saying is, I don't need to know what well-formed formulae are true up to this point. I don't care. I can create a one that has to be true. Just give me a phi that is a well-formed formula. Doesn't have to be true to begin with. But if you do an or between that well-formed formula and the negation of itself, the resulting disjunction has to be true. Does that make sense? Yep.
Fine, you said it has to be well formed in this case.
It has to be well-formed, but it doesn't need to be known to be true. If it does not appear on the left-hand side of the infer or the inference, then it just needs to be well-formed.
But the phi and the psi on the other inference.
They're independent. This is one rule, this is another rule.
Yeah, but in that other case, the phi and the psi are known to be true.
So in this case, because, in the first rule of zeta, because the set phi psi is on the left-hand side of the inference, so that means the expression phi and the expression psi, they have to be one, well-formed, two, it has to be known to be true at a certain point of the entire system of running the system. Okay, so I can make another one. Yep.
But we also have phi as negative phi, and because phi.
This is not and, this is or.
So if it doesn't have it, then you can have it as or.
This is completely syntactical. In other words, I don't really care about the meaning of the operators. Okay, let me give you another example. I think this one would be, it might make it more clear. So the other one, is going to, so everything is going to have this particular format because you have the left-hand side containing a set of patterns. So each element on the left-hand side is going to be a pattern that you're looking for, but you can have multiple patterns that you're searching for at the same time. Out of those patterns, you can basically do a transformation. So you can look at the little V dash symbol as T, because if you look at it this way, it looks like T, it is transforming, okay? It is a transformation. So now let me go with something like this, okay? This one is gonna be negation of phi or psi over here, backslash. That's one pattern I'm looking for. And then the second pattern I'm looking for is phi here. And then what I can transform in this case is to say psi has to be true. Now, this one does resemble something that we know from the iota already. But in this context, it is a simple transformation rule. All it is saying is, I'm looking for two things, okay? Because remember, the left-hand side of the inference is specifying what I'm looking for. I'm looking for two patterns. The first pattern has to be an or, and then one side of the or is the negation of something. On the other side of the or is just something. Can they be the same thing? Sure, it's not going to be very useful in that case, but they don't have to be the same. Is that okay? Once I find the first pattern, the second pattern doesn't have freedom anymore because this phi has to be exactly the same as that phi. I'm looking for two well-formed formulae known to be true at this point in time. One has to be the or between some well-formed formula and the negation of some well-formed formula. The second one has to be the same thing as the negated well-formed formula on the left-hand side of the or that is being negated. In other words, I'm using constraints, okay? If they refer to the same Greek symbol, they have to be the same. If they're not referring to the same Greek symbol, they can be any well-formed formulae that is known to be true. Is that okay? Yep.
I'm just confused on the inverse symbol. So does that mean like it returns?
It marks, it basically marks this also as known to be true now.
So that's the new, that's what it transforms into, is what you're saying?
You're looking at a patient like this. You're looking for a patient like this. And then you say, oh, you know, this patient here is going to get infected now.
Okay.
This is how the quote unquote disease spreads.
Okay.
We're specifying, you know, how the disease spreads.
Then for I, if that negated P was just P, that's not well formed.
Hmm?
For I,
Yeah,
if that negated P was changed to just P or Q, that's not well formed.
it would still be well formed, but it would not be useful in our example. Because in our example, because we have this rule over here, we can apply this rule once. And then we say, oh, if I just make this P, you know, to take this place of phi, and I take this Q to take the place of psi, then phi, you know, phi by itself is also known to be true and is well formed. So now I have satisfied both constraints on the left-hand side of the transformation. What do? Well, we pass this disease onto the new pattern here. The new pattern is just saying, oh, whatever psi is out of this entire pattern, and you remember that we use Q to put into the place of psi. So now we can now say, you know what, psi, I got bad news for you. You're also sick. This is basically how we spread the truthfulness of well-formed formulae, starting with our patient's zeros in iota. Yep.
And does it have to be symbols or is that just does it have to be Greek symbols?
Well, it makes it easy to differentiate because the Greek symbols are only used when we specify the rules. And then the English letters, they are used to refer to variables. So P, Q, R, S, T are basically variables. We don't know whether they're true or false or not, unless they're in iota, obviously, by itself, but they're called variables. The technical name of the Greek letters is they're called schematas. They're basically placeholders from a syntactical matching perspective. They're kind of like wild cards. Yep.
Then the goal is to try to find if Q is true or if it's well informed.
Whether it's true or not, Q is already, everything in this set are well formed to begin with. We want to know whether it is true. So in this case, I can apply that one single rule. Okay, let me just finish this and then we're all good to go. So we will do this so we have phi on one side, okay? So we have not phi or psi, that's one thing. And then we have phi all by itself, right? So now we say, if I make P the same thing as phi, it has to go to both, okay? You cannot have your phi instantiated to one thing and then have the other one instantiated to something else. And then we go like, okay, Q can go here. So now I have just matched the left-hand side of the transformation. Yep, go ahead.
Wouldn't that P go to the right-hand side? Instead of negative P going to 2, wouldn't the P on the above would go to the right-hand side?
On the right-hand side of, yes. So now your transformation sets psi, by itself, also it should be marked as true. So we look at what psi are we talking about? Psi is our Q. So this is the result that is marking this Q as also known to be true. So this is a application of the transformation rule. Now in this case, I made it very simple because everything that we need to use the transformation rule is already in iota, but it doesn't have to be. So in other words, I can take the result of this, apply another transformation, and then take the result of that, apply another transformation. The objective is, if I give you a particular well-formed formula, can I eventually mark it as known to be true? So in this case, I can give you this question here. This S here is standing all the way out here. The question is, can I eventually mark it based on what is in iota and based on what is in the set? Yep.
I'm just, because you pointed negated P to both negated, is that psi, the the 0.
Yes.
You pointed negated psi and would you point the p to the psi?
P is going to psi alone, not p. So it is psi is associated with p all by itself, not p. So psi is basically p. Phi is p, and then psi is q.
So what's the use of that p on the left-hand side, the dot, the bullet point?
This one?
Yeah.
Because this also goes to the same places. Because this p has to agree with this p because they're both used to instantiate phi. So basically, I did not draw the link, but if you were to draw the links, it would have been like that. Yep. So to summarize, I know we are out of time. To summarize, it's a pattern matching kind of deal. Okay, it's just syntactical, looking at things. Okay, can I find this pattern here? Yes. Then I would take certain things from these patterns and then make the other side and say, you know, that thing over there, that is also known to be true now. And then I can, you know, repeat this process. The question is, can I eventually go to a thing and say, yeah, that has to be known to be true. But in this case, S cannot be known to be true because of iota. But the question is, you keep searching in the haystack. In this case, the needle is not even in the haystack. How do you know that you have searched enough in the haystack to make that conclusion? Instead of saying, well, maybe if I search for another hour, another century, or another millennium, I will be able to find it. So that's the problem with this approach. Okay, so next class, which is going to be our exam, next Monday, we'll come back and talk about this. So I think the recording is going to come in handy. Okay, give me a second.
50-50 on this, like,